This conference will now be recorded.
So hi everyone, thanks for joining. This would be last meeting for February. And before we get into the main event for which uBlocks is Samuel kindly volunteered to present, let's go over some of the updates on our work with TAP. So the good update is that we're getting ready as a project to get out of incubation with the and towards a general TAP project, and we're gathering the specs and the drafts from the work streams. The first two work streams seem to be shaping up and able to provide draft specs in time. So we're going to work with the volunteers of every work stream and finalize these drafts and work behind the scenes also with the OCP team to get this project up and running out of incubation. There's going to be a good discussion happening with the OCP networking team in early March around the PTP profiles and the interaction with, well, switching networking. That's going to be March 8th, and I believe I sent everyone the dates and time for that. So we would like to see the volunteers and definitely the rest of you joining and sounding your feedback. And then for March, when we're going to have the next call in March, we will be dedicating the call to the oscillators workstream. This is the first, that will be the first focus session on hardware. We're going to set the goals and we look for volunteers who want to take active part in this discussion, focused in helping classify the hardware characteristics of components in the different, according to different use cases and according in the data center, different locations in the data center. So that's going to be very exciting work we're going to do on the hardware aspects, and we are looking for everyone to chime in and support us here. So that is more or less what is going on with our work streams and where the progress is. If you have specific questions for each of the work streams, don't hesitate to contact us, and we will provide that. Second item on the agenda would be the hackathon. We have discussed early on how we want to bring our minds and talents into solving into coding and then solving some of the more interesting and issues that we don't get to in our day-to-day work. Ahmed, my peer, would you like to elaborate a few minutes on the hackathon and what we are planning for it?
So for sure, yeah. So with respect to the hackathon, so like we're doing, like, let's say, a lot on the why, sorry, on the how. Like basically we're bringing like the PHC in all this NICs distributed in the system, let's say in Datacom context, synchronized, let's say, with a grandmaster. But we are thinking now more, let's say, on the why. So we have a lot of applications already lined up, but we believe that this is basically the tip of the iceberg. So therefore, we're thinking, like, let's have a platform where we promote new ideas, and we're really looking forward for both, like, industry and academia, where we can have, let's say, like this session, let's say somewhere we're thinking about, like where in the calendar it also fits well, like, let's say, academic friendly, where like the, let's say, final exams are done, and then let's say somewhere probably in the early academic calendar summer, basically right after the exams, where there will be, let's say, in April, so let's say early May or something, we'll have like this session. And we're looking also for volunteers, both, let's say, sponsors, volunteers. If you want to have, let's say, I don't know, your company wants to, like, let's say, have some like promotions there, and they want to have, like, let's say, the price or something, please reach out to us. That would be greatly appreciated. And we don't want to have it like always like Facebook NVIDIA. Like, we want to have, like, I don't know, other parties as well, like, helping with this. And just like to just give you a nugget basically to think about, like, most of PTP today is basically designed obviously from the early supporter that it had, and that was telecom. So you basically have the PHC synchronized with the grandmaster producing this PPS pulse distributed in all the nodes, and then everything else, the electronics basically takes care of this PPS pulse, and that's how you're taking advantage of this accuracy that you're bringing over the Ethernet to everywhere. But when it comes to datacom, we pretty much are leaving it there. Like, you have the PHC sitting on a device on the PCI bus, and that's it. And like, bring it back into user land, you're like losing pretty much all this accuracy, this precious accuracy that you brought with all this like techniques all the way to that point, to the PHC. So what we were thinking is, like, there are a lot of techniques, like a lot of methods, a lot of, let's say, utilization that can be done here, and we just want to give everyone the opportunity to think about it. If you want to think about, like, what details like we have in mind, I was thinking about something like NASA Space Apps Challenges, which is like a 2-day session where you bring, let's say, I don't know, people thinking about things and so on. First day is like pretty much you work on the proposals and everything, and then you have this, like, say, 24-hour of like you suss out the ideas and everything. Obviously, you cannot implement these things. They're more like, if you can come up with some MVP, that was fantastic. But again, this is not so easy to do.
Ahmed?
And then in the end, you will have, like, basically the judgment. Yes, go ahead.
I want to give maybe a little teaser or explanation of how do we see it. So we will theoretically, the hackathon will be we will have like servers connected back to back with all the timing capabilities. So we will come and we will synchronize those servers, and hackathon teams will come. They will run an application, measure performance or something, and then they will change the code in order to leverage the synchronization and measure the performance again.
Yeah.
So you can propose any application that you find suited. In the proposal, we want to see what is your speed of light, like what's the ultimate performance goal that you think can be reached, and what you think is expected target. And you can come and enjoy those hardwares. We will provide x86 connected to a synchronized system. We will have our architect helping for you to port it in. And if you need any special equipment like a GPU, you can also ask it for in the proposal and so on. So this is one thing. You can come with your own application, run on this facility, demonstrate speed of light, performance acceleration, and you will get a huge stage, maybe even a trophy. Let's speak about this later. We are considering to offer also another hackathon path for people who wants to actually improve the synchronization facility, like people that wants to work maybe on the PHC2C services or on the PTP4L and things like that, to show even better open source synchronization capability. That is also doable.
Thank you, Dotan. Thank you, Ahmed.
Welcome.
So this sounds really exciting, and there's definitely a lot of logistics that we need to prepare to have that, and also the good collaboration from you and your member and your teammates and the academy that we wanted to invite. So I guess we'll work on it more and share the details as we go along. And
Yeah. We will soon create a poster reaching out for proposals, and we will publish it. We need your assistance to spread the rumor out. It's going to be a big thing, because you don't you don't have the access to such state-of-the-art synchronized system any day, and you can actually implement anything that you think of.
So I mean, just to add to what Dotan is saying, it can be both beneficial, let's say, for the industry and academia. Like for academia, like, okay, now basically you have a platform where you can show to industry what you can do, all your ideas and everything and so on. And for industry, well, you have the opportunity to see the latest and the greatest, and feel free, you have all this pool, you can hire them, license them, whatever you can do. Like, so we're just providing this matchmaking, basically put all these things all together and let everything happen like naturally.
Yeah, everything eventually going to be public. All the results, all the codes is as according to the Open Compute regulation. We will post the first 3 places at a good spot in our web page, and we will try even to promote it in the next ITSF conference, maybe to give an overview to the community what we have done. So we do expect a great exposure for those.
Sounds great. Thank you, Dotan. Thank you, Ahmed. Okay, well, I'll ask if there are any questions or comments from the team, from the TAP members before we go to the main event. Let's see if there are any questions. Okay, so for today, we have the pleasure of hosting Samuel from u-blox. This little slide I stole from u-blox presentation. So just I'll turn to Samuel if you would like to introduce yourself and your affiliation and what you're gonna discuss. I'll share with you I'll give you the screen control once you're done.
Thanks a lot, and thanks for the invitation, and thanks for the opportunity to come speak to you tonight. I also have on my deck the very same slide, but never mind. So yes, my name is Samuli Pietilä. I joined u-blox 4 years ago, 2016, in the product strategy team for the positioning and timing team. At the moment, I'm responsible for the u-blox GNSS timing product portfolio. Before joining u-blox, I worked for 20 years at Nokia and a few last years at Microsoft in the mobile phone side of Nokia in several positions related to GNSS technology. And also I have a Master Science degree from the local university here in Tampere, Finland, and I have also written a few patents with my talented colleagues.
Thank you. I'll make you the presenter now, and you can drive from your screen.
Yes, let me see. I need to click here. This one maybe.
I can mention that I've been in Tampere 5 times, and you need to skill your study nights capabilities. Study at the dark.
Okay. Good. Welcome again. So can you see my screen now?
Yes.
Okay, cool. Then I will need to, maybe I put it to full screen mode for your benefit. Like this. Okay, let's go. So this slide you already saw, so we can skip it. So what I thought I would speak today quickly for those who are not familiar with the company u-blox, just a few slides. And then we talk about the GNSS timing, firstly, very basics. Some of you maybe, if you watched the webinar that I gave last year, you might recognize some of the slides stolen or borrowed from there. Then we talk about the multiband GNSS, what it is all about, why we want to do this, and then some slides about the threats and defenses. that we are seeing today in the GNSS area. And finally, I have just one slider about the portfolio that we are offering. So let's see, how much time do we have?
Until the end of the hour, so 40
okay,
minutes.
fine, good, okay. Should we just, if any questions pop, just interrupt me and ask while we go on. So maybe that is the best way to approach. Okay, quickly about the u-blox. So it's a company founded in 1997 in Zurich, Switzerland, as a spin-off from the local university of technology. Last year revenues in Swiss francs about 380 million, roughly the same in USD as the conversion rate is almost 1-to-1. We're serving quite large customer base, more than 7,000 customers worldwide in 3 core markets, namely automotive, industrial, and consumer markets. We have a little bit over 1,000 employees, out of which a vast majority is in R&D positions. The company was listed in the Swiss Stock Exchange 2007. We invest quite heavily in R&D. Last year, over 20% of the revenue was invested back into R&D, and the company has been growing annually about 3% over the past 5 years. We are a global company, so we have presence. We have offices in US, Europe, Asia, Australia, and here is the Finland office where I am.
Almost under any satellite.
Yes, actually I'm not in the office tonight. I am at the home office, of course.
Yeah.
Okay. And then what do we do at u-blox? So what we do, we make integrated circuits, so chips, and also then modules based on our own chips for positioning. So this is GNSS, basically the product center where I am working, but also then we have 2 other product centers, cellular communications, and then also short range, meaning Wi-Fi, Bluetooth radios. And then on top of hardware, we have then also services that are also available from the company. Okay, that was very quickly about u-blox, the company. So we can go to the main topic, the GNSS timing. What do we mean when we talk about GNSS timing? What it is all about? So as you probably know, so the satellites that are up in the sky, they are equipped with very high quality atomic clocks on board. Actually, they have several for redundancy, as they are under quite heavy environment on the orbit. So they have 3 or 4 clocks actually there. And the satellites, they are very well synchronized to a universal time, which is maintained by the ground control stations. So on the ground control station, they have the master clocks, and then they use this time to synchronize the satellites. And then the receivers, the GNSS receivers, when they receive the signal from the satellites, they can take advantage of these atomic clocks and provide time within nanosecond level kind of accuracy. Even though the receiver itself does not have any atomic clock, it has only a very cheap crystal oscillator inside, TCXO typically, something like this. And what is this then used for? So this can be used when we talk about timing. So we can use this, or our customers use it for synchronizing different things globally, typically some sort of communication systems, networks, power distribution networks, financial institutes use it for timestamping the transactions and so forth. Wherever you need an accurate time, which can be traced back to the UTC time globally. So GNSS timing, what is it? How is it different from the normal navigation? So here I have for illustration the navigation GNSS receiver, like the sat nav you have in your car or your mobile phone, which is telling you where you are. So in case of the navigation GNSS receiver, it's always a problem of 4 unknowns to be solved: the latitude, longitude, altitude, and then also the time. And from some high school math classes, we remember that if you need to solve 4 unknowns, you need to have 4 equations. So basically, you need to have 4 measurements. So in this context, it means you need to have visibility and measurements. You need to be receiving a signal from at least 4 satellites. Then you can solve these 4 unknowns. Obviously, if you have more satellites, the better. Then you have overdetermined solution. But as a minimum, 4 will be needed always. But when we talk about the timing receivers, here we make one fundamental assumption. We assume that the receiver is stationary. We assume that the position is fixed, and we also assume that it is known. So we know the coordinates. And then the problem turns into quite different one. No longer you have 4 unknowns, you have only one unknown remaining. You only need to solve for the time. And that's it. That is the assumption we make, and therefore we can do the timing receiver.
So that means that you can do it with 1 satellite?
Yes, exactly. You are already on my next slide. So what are the benefits then? So I give you here 4 benefits. Why do we want to do this? The first obvious benefit is that since you don't need to solve the XYZ, the coordinates, you can use all the satellites that you have available, all the measurements you have available, just for that one unknown, for the timing. It means you get always 4 times more information. So in some simplification, you could say that you have 4 times more measurements that you can average to get actually the time. And this means that your time solution will be much more accurate. But as you already pointed out, you can also turn this the other way around. You don't really need 4 satellites anymore. You can do it with 1 single satellite. This is enough. 1 satellite, 1 measurement, 1 unknown, the time. So if you are in some urban environments where your antenna is somehow in a challenging location, you don't have a good sky visibility, you can still provide the time output even if you see just 1 single satellite. Obviously, the accuracy is not as good as if you had all the satellites in the sky. Then you would get the benefit of averaging over all the satellites, but still, it's pretty good timing with just 1 satellite. So it gives you kind of improved availability of the service. What you can also do is so-called TRAIM, the timing receiver autonomous integrity monitoring. So inside the receiver, there are algorithms that are running and constantly monitoring the integrity of the received signals, trying to detect any faulty satellites or outliers or otherwise measurements that are not fitting into the solution. Now, of course, you can do this with a normal navigation receiver as well. Then it's called just plain RAIM without the T. But when you have a timing receiver, then you can do a little bit more. You can do a little bit better because you don't have any more the uncertainty of your position. And this means you can better detect the outliers, and also in case of less satellites, you can still detect the outliers. And finally, also, obviously, later today we'll talk about spoofing, but in case of a stationary receiver, if you suddenly start to detect something, some movement, you immediately know that now something funny is going on. Your antenna on top of the mast or wherever it should not be moving. So you can raise a flag that now there is something funny going on, and let's maybe not trust the output at this point of time. Okay, these are the kind of 4 basic benefits in a simple terms why we want to use a timing receiver. How do you enter the time mode? Maybe you wonder. So obviously, if you know the coordinates, you can directly enter them into the receiver. Maybe you know them from, I don't know, local land surveyor during building, the construction time of the building or the mast or whatever. If you don't know, the receiver can still find it out for you. This is the process which is called surveying. So the receiver would then automatically determine the coordinates, the fixed position coordinates. So you would install the receiver, install the antenna, and then start the surveying process. You would need to define 2 parameters: how long you want to run the surveying and what kind of position accuracy you are after. And then the receiver would go on navigating, calculating the position until it is meeting both of these conditions. Receiver sees that the accuracy is now met, and also the duration that you asked for is reached. Then the receiver is kind of making a decision that, okay, now I know the coordinates well enough, as well as I was requested to. I will now switch to time mode. I will stop 3D navigation and start operating in time only mode. Okay, that was very quickly the basics of the GNSS timing receivers. Any questions so far? Okay, then we continue to the multiband side. So if you look a little bit back on the history about the GNSS and the multiband GNSS, so since the very beginning of GPS, even the first receivers, the military receivers, they were always dual band. GPS provides a signal on 2 different frequencies, but until some years ago, the second signal was only this encrypted military signal that was only kind of available for authorized users who had the necessary keys to decrypt the military signal. Also, in the past, there were a few applications like the land surveying here that were using dual band technology. They were using the military signal using so-called codeless techniques. But this had some quite severe drawbacks, and it could be only used under certain conditions, like here you need to be stationary and have good strong signals and wait for a long time and so forth. So never really any kind of mass market or consumer kind of applications to make it really popular. But things started to change in 2005. The first GPS satellite was launched that was capable of transmitting the civil signal on the second frequency as well. This was the so-called GPS L2C signal. Obviously, one bird does not make still yet the spring, so it took quite some years for the GPS to grow the constellation of these new satellites that provided the second civil signal. And now finally we are reaching the level where it's starting to make sense to take it into use and integrate into more wide range of receivers and a wider range of applications to take the benefit of the multiband technology. Here I talk about GPS, but maybe worth mentioning also that, for example, the European Galileo system, since beginning it was designed to contain a civil signal actually on 3 different frequencies. And also the Chinese Paidu and the Russian GLONASS system, they have a second civilian frequency available as well nowadays. Okay, so if we look here, it's a bit busy slide, but trying to illustrate the different frequency bands and different signals that are actually available today. So if we start here from the right side, so this is the so-called L1 band. It's around 1575 megahertz, and here we have the very first GPS L1CA signal. This is the signal that started the whole thing, and the signal that the legacy GPS only receivers have been receiving since the very beginning. Gradually, other systems came to the same L1 band. Firstly, the Russian GLONASS, and then later on the Chinese Paidu, and also the European Galileo. And then at this point, the receivers started to be so-called multi-GNSS receivers. So they would receive several constellations from the L1 band, not anymore just GPS or L1CA only, but 2, 3, 4 constellations from this L1 band. Then, as I mentioned, so the second and third frequency signals started appearing. The first one was this GPS L2C here, and nowadays GPS has also this L5 signal here. Today, there are actually 23 satellites that are providing this L2C signal, and 16 satellites providing the L5 signal. So not quite the full constellation, the full 31 satellites yet, but now the number of satellites starts to be reasonable, so that it makes sense to start using these signals. GLONASS, the Russian system, it has full constellation, so all the satellites support both of these signals, the L1 and the L2 OF, open FDMA signals. Galileo today has 22 satellites operational, and all signals are available in all satellites. So basically 3 civilian signals available from the Galileo satellites. At the moment, Galileo is still in so-called initial operation phase, and we're expecting to see the full operational capability later this year, as they launch probably 2 more satellites and then declare it as a fully operational. And then on Paidu side, so here we have Paidu is also going through upgrade phase, or actually completed the upgrade to Paidu generation 3, which means that this P2I signal here was phased out, or is being phased out, and is replaced by these P2A, B2B signals. And especially this P2A signal here, which is sharing the same frequency with the other signals here on the L5. This is available globally from 24 Paidu 3 generation satellites. So also there we have a very good coverage. Okay, so this is kind of the playground where we have the signals on different frequencies. Now, why do we want to do this dual band? So the biggest benefit is in terms of the ionospheric error compensation. So it turns out that the ionosphere, one layer of the atmosphere, is as the name kind of implies, it contains free ions, so basically charged particles that affect the radio wave propagation. As my simple picture is here trying to illustrate that as the radio wave travels through the ionosphere, there will be some some distortion which causes incorrect range measurement at the receiver, which means then some error in the position or in the timing output. But it turns out that the impact depends on the frequency, or the carrier frequency of the radio wave. And what it means is that if you are observing it at two different frequencies, you can actually, after some clever calculations, mitigate the effect of this ionospheric error or the ionospheric variation. This is something that you cannot do with a single frequency. You get only one observation, but if you do it on two different frequencies, this is possible. And then the further away these two frequencies are from each other, the better you can do it. The ionosphere conditions, they vary depending on different factors. This is due, the ionosphere kind of variation is caused by the radiation from the sun. The radiation from the sun is the one that is detaching the electrons from the atoms or the molecules. And this means that depending on the amount of radiation you get, the conditions of the ionosphere are changing. So during daytime or nighttime, you have a different conditions. During wintertime, summertime, you have a different conditions. And also depending on the solar activity, the sunspot activity, you will have different conditions. So it is never stable, it's constantly varying, and therefore it's kind of causing an error that is varying, and you want to compensate it away. So I mentioned the ionospheric errors because of the solar cycle. So just kind of heads up for you guys, maybe that there is an 11 years long cycle on the solar activity. Here is a picture from NASA showing it and illustrating that actually this here where we are today, we are at the minimum. It means that the ionosphere is very quiet, very smooth, and it means that the GNSS performance today is very good. It's at the optimum point. And just to be aware that once we hit the next maximum somewhere around 2025, the performance might be or will be different. Okay. Maybe
every 28 years the sun goes to the original. I mean the sun cycle is 28 years. Every 28 years it go back to the same place. There is a 28 years cycle. So I don't know. We don't have enough GNSS history for that.
Yeah, this I don't know. Yeah, this is just the sunspot activity on a 11 year cycle also.
Mm-hmm. So Samuli, does this come with a recommendation towards 2025? Is that something we're?
I think the recommendation is that something to keep in mind. Whatever you measure today, take it with a grain of salt. So what you're seeing today is optimal. So maybe if you
sell everything before 2025.
whatever you do today, leave some budget, leave some margin for the when the things get worse. I think this is the message.
Okay.
Okay. So here is some data from the Galileo operator from Europe about how big the error is from the ionosphere. So in a single band receiver, it is somewhere between 3 to 6 meters, depending on the elevation angle of the satellite. And you can see this is actually dominating. All the other error sources are way smaller. But once you add the multiband, you see it goes down to something minimal 3 to 8 centimeters. So it is not anymore kind of relevant. The other error sources are bigger. And if you, in case of timing receiver, so you maybe want to convert in your head this to nanoseconds. So this would be somewhere between 10 and 20 nanoseconds, this error here on this side, and here nothing, I don't know, picosecond something.
So it's
Okay,
it's like
just
the same formula, 5 nanoseconds per meter, or
three
just
3 nanoseconds per meter. Yeah.
3
Or
nanoseconds per meter.
yeah,
Okay.
or 3 meters per 10 nanoseconds. It's a speed of light, 300,000 kilometers per second. There you
Okay.
get it. Yeah. Okay. But okay, so the ionosphere correction is like the main driver, but also a few other benefits. So firstly, keeping in mind that the original, the very first GPS L1 CA signal was actually, CA comes from the CORS acquisition. It was really designed for the military users as a signal to acquire and then hand over to the more accurate precision military signal. So it was never as so much designed as a navigation signal. Even the name is CORS, so it is not as good as the military signal. But the modern signals, the new signals, they have a very different starting point. They were from the beginning actually designed for civilian use, designed to improve the performance of the civilian receivers. What they have is 10 times wider bandwidth, which means that they will provide improved accuracy and improved multipath performance. Here one drive test we did with I think this was done in Zurich, in Switzerland, and you can see the L1 only when you're between the buildings is a little bit off, but once you come here in the open area, then the L1 also finds the truth, but the L5 is nicely smoothly on the right lane on all the time.
Samuli, maybe I can ask like a technical question a little bit in detail. I don't want to go too much. So you have basically, let's say, this mechanism that you're finding your distance basically from a satellite, that the position of the satellite, since it's in geo, it is known. And then you have basically a lookup table that you go through that. That mechanism that you use to determine basically the distance is basically like a correlation you do with like other signals that they come through. Is that right? You look for the phase difference, right?
So firstly, the satellites are actually not geos. They are on a medium Earth orbit.
Oh yeah, medium.
Yeah. They're traveling like 4 kilometers per second. Yeah. And we have the orbit parameters. So when we know the time, we can calculate where the satellite is. Inside the receiver, it's a CDMA receiver. So there's a correlation where we compare the local replica against the signal that we're receiving, and once we get those aligned, then we know we are synchronized with the signal. So then we know the kind of it's called it's not really a range measurement, it's called pseudo range, because we don't know yet the accurate time, but once we solve the time together with the coordinates, then we get the also the actual range measurement.
So now that you have a lot of like different constellations, can't you do these things, let's say from, let's say one satellite from, let's say L1, one from L2, like is that possible? Like, or you have to do all of these things only in one?
I'm not sure I quite understood the question, but the
so let's say one you want to do like to basically get these correlations, like this triangulations in the end.
Yeah.
Can you measure, let's say, the signal received, let's say from a GLONASS satellite with a signal from a, let's say, from GPS?
Yes. So we need to do a little bit trick there, because all the systems they are running on, they have their own master clocks, their own control stations, so they are not on the same time base. So what we need to do is first we need to figure out the time difference between the systems, and then we can put them onto the same time base, and then we can use them as we like, mix and match.
Sure.
Yeah.
So every constellation has its own master clock, you say, right?
Yes, sure. I mean, the American GPS, they have it's the US Air Force who is actually controlling it, and the Russians are controlling their own system, and Chinese are controlling their own system, and
then European, the difference is known, or is it like constant, or the difference also changes?
No, it is constantly changing because they all have their master clocks at the ground stations.
Yeah.
So it is something that we compute. Once we're receiving GPS and say GLONASS, we can see what is GPS time, what is GLONASS time, then we can calculate the difference. And after that, we can then mix and match the satellites.
Thank you.
Samuli, just a quick time check. We have a little bit more than 10 minutes. Should we jump into, some of the later trends and solutions that you wanted to cover?
Okay. Yeah, I'll pick up space. So you wanted to hear about the jamming and spoofing?
Salat, if you don't mind, let someone basically take his time and then present as much as possible, because we're gonna have the session recorded anyways. I don't want to lose on the all this material.
Sure.
Samuli, take your time. We're gonna give you
Okay.
as much time you need. And everyone else, if you have to leave, that's fine. We're gonna have it recorded anyways.
Okay, thanks. Yeah, it's also getting late, so let's see how long my brain stays awake. Okay, so one last thing I wanted to say about the multi-band GNSS, the benefit is in terms of the jamming and spoofing. So in case of one of the bands getting unusable for whatever reason, the benefit obviously is that you have the second band, redundant band, which you can then continue operating. Okay, that was quickly it. So threats and defenses. So
sorry, just one question before we jump to the next section.
Okay.
Do you cover any more on the augmentation systems? I mean, like Quasi-SS or EGONS or any of the other ones, or is that out of scope for the presentation?
I did not really plan to talk about those. I briefly
I was just
showed
wondering
them.
how you use them within the. I see it on that slide, and I was wondering if you could pick up on that.
Here we have Navic. Here we have Quasi-Zenith. So what was the question then?
No, the question is more about. You've explained how you use the different signals from the different systems and interpolate them, but I didn't know if you're going to also talk about how you use the augmentation systems in order to increase accuracy or services.
So the Quasi-Zenith system and the Navic system. So the Quasi-Zenith system is in Japan and the Navic is in India. So these systems are used just like the other major systems, with the exception that they are only visible in their target areas. So if you are in Japan, we'll use then the Quasi-Zenith as well. This is the way it works.
Okay, so that there's no special additional secret sauce that you add to the interpolation versus the regular systems. I mean, there's some areas where you can have extra coverage. What were the benefits? That was more the question. But if it derails your presentation, we can park it.
Yeah, the benefit is that you get more satellites. You get more satellites overhead, directly above you. So even in urban canyons, you can assume you can see still a few more satellites, which in some cases is just what you need to get the fix. Otherwise, there is no difference. I mean, Quasi-Zenith, for example, is I would say almost exactly as GPS. All the signal specification, everything is the same. So.
Okay, and in terms of reducing acquisition time, I mean, I assume that plays a role.
Well, not really. No. I mean, Quasi-Zenith signal is the same as GPS, so it is acquired at the same pace.
Okay. Thanks.
Cool. Okay. So threats and defenses. Here I was. So firstly about the jamming. So some definitions. So interference is like something unintentional. Maybe there's an electronic device malfunctioning and radiating emission on our GPS frequency band. Jamming is then a more evil thing. This is intentional interference. Somebody's trying to deny the GNSS signal reception. And maybe most or one of the most common cases here is this so-called privacy protection devices, like this example here that are blocking the GNSS frequency, and of course maybe then causing collateral damage. So whatever other receivers there are nearby, they will get also hit, even though the original intention was maybe only to block his own tracking device. So what are then the defenses against this kind of thing? So firstly, it's good to remember that the L1 and L5 frequency bands, they are by the International Telecommunication Union, they are reserved for aeronautical radio navigation service. So it's clearly illegal to start any jamming on these bands, and also it will be quite strictly monitored, as this is used also for the aviation. So there will be consequences. But of course, sometimes this could happen. So what we have in the receiver, firstly, we have the filtering within active antenna, and within the RF front end of the receiver, we have so filters typically that are taking out any out of the band noise and interference, like for example, there could be a cellular base station or a TV broadcast station or whatever that is not transmitting on the GPS band, but on some neighboring band. So those are filtered out. One step more difficult would be then interference or jamming that is in the GPS band. Then this we cannot anymore filter out without affecting also the GPS signal that we want to actually receive. So commonly this is done with the filter banks inside the receiver. So very narrow filters that you can control specifically targeted to take out CW kind of sine wave interference, or maybe some sweeping chirp kind of interferences. And then thirdly, as I already mentioned, so redundancy in the receiver. So if one band, one frequency is blocked, then in case of multi-band reception, you can then continue operation on the other band if that is still clear from the jamming. And then a little bit more advanced threat is then spoofing. So here the definition is that somebody is transmitting a fake GNSS signal in order to make the receiver output incorrect position, velocity, or time, and in some cases even so as determined by the attacker. So he wants you to see the position he's controlling you to be. One form of this is so-called meconning, which is actually like a rebroadcasting, recording signals at one place at one time and then rebroadcasting them afterwards, and making the receiver then again be in wrong place or wrong time. And sometimes this can be combined with the jamming, so that firstly the receiver is jammed to make it lose all the real signals, and then bringing in the spoofed signals, so then these would be the only signals that the receiver sees, and trying to get it confused like that. Obviously inside the receiver, so there are algorithms on several levels. It could be on the radio frequency level, or on the signal processing level, or on the navigation level, trying to detect any abnormalities in the signals and events that are happening there. And also then something that is coming from the Galileo system is the Open Service Navigation Message Authentication. So this is maybe the first real attempt from the satellite side to provide this protection for civilian receivers. Obviously, on the military side, you have encrypted code, so these are really difficult to fake unless you know the keys of the military signals, and therefore probably not going to happen. But on the civilian side, because all the signals are kind of known, it is easier. But here, what Galileo is doing is they are actually adding a few bits of signature in the message that they are broadcasting. And then the receiver can, with the public key, check that the message is authentic, and therefore it can be sure that the transmission is coming from actual Galileo satellite and not a spoofer. This is still not perfect. This is authentication of the navigation message, so it's not the full signal, but clearly it's a big step to the right direction. And we are waiting today this is in test phase, and it should be in operation in well, I think maybe next year, to be seen how the Galileo schedules will turn out. Okay, then I have still two slides about the threats. So the previous threats, jamming, spoofing, they involve the outside attacker trying to interfere with your receiver. But there have been cases also where there have been failures of the satellite system and causing trouble. So the latest major event was the outage of the whole Galileo system in July 2019, where the service was unavailable for over a week. Here what happened was there was a failure in the ground segment that prevented updating the navigation messages that the satellites are broadcasting. And what this means is that then the navigation message is the orbit parameters are valid only for 2 to 4 hours. So quite quickly they expired, and any well-behaving receiver would stop using those Galileo satellites for navigation purposes. So if somebody had a Galileo only receiver, it would have stopped at this point, but this kind of receivers are extremely rare, and any multi-GNSS receiver would continue navigation without problems, because of course there are redundant GNSS systems, GPS and others that could continue without an issue. So in this case we were lucky, it happened with Galileo. Of course we have not seen this kind of issue with GPS. But if that would happen, there might be still quite a lot of GPS-only receivers out there that would be then in trouble. And maybe to say in benefit of Galileo, of course, as I mentioned before, Galileo is still in the initial services phase, so it's kind of, well, not maybe accepted, but it is still understandable that in this phase, there might be still some hiccups as they are still building up the system. Another famous incident was with GPS in 2016, when there was an issue with the UTC conversion parameters that the satellites are broadcasting were incorrect for about a day in January 2016. So here, as a background info, so the GPS system, the GPS ground control segment, the satellites and the receiver, so they're all operating on GPS time, not on UTC time, but on the GPS system time. And then the GPS broadcast contains a set of parameters that the receiver can then use to convert from GPS time to UTC time. And if you apply these parameters, then the receiver can provide a UTC, United States Naval Observatory version of the UTC within a few nanoseconds. So here, the problem was only in these conversion parameters. So the receiver that was using only GPS time, for example, any navigation receiver, they would be perfectly fine, no problem at all. only the receivers that were configured to output the UTC time would then see this incident. But here again, redundancy helps. If you had a multi-GNS receiver, it would have been possible to detect this issue. And in this case, it was also so that actually the GPS broadcast on the second and then third civilian frequency on the L2C and L5 signals was not affected. So also multi-band receiver could have picked up this issue. Okay, and I think we a little past the hour, but this is now any questions on this side, these topics?
Samuel, like I'm wondering, like, what do you see the future for like further constellations? Like, would we have, let's say things like, let's say, SpaceX Starlink, which is like LEO? Would they ever think like have also something like this, like both like timing, or let's say if not navigation, timing?
Yeah, this is interesting topic. I don't know what Elon Musk has in his mind, but yeah, I have seen some papers speculating with this kind of idea that you could actually get the from these LEO satellite constellations, you could get also this kind of service.
Yeah.
I'm not sure if the Starlink satellites are designed for this kind of operation, but maybe some other system could be.
Yeah, perhaps you would know better, like before everyone else.
or maybe the whoever is planning to build this. We only build receivers, not satellites.
Exactly. Yeah.
Yeah. Okay. So my last slide. So quickly show you the portfolio that we are offering today. So here on the left we have the u-blox 8th generation. So the Neo M80 and the Lea M80. So these are single band L1 band receivers, multi-GNSS. So GPS, Galileo, GLONASS, and BeiDou capable, 20 nanosecond timing accuracy, 2 time pulse outputs, configurable frequency, and with the timing features that we spoke about in the beginning, the surveying, the single satellite, the DRAMs, and so forth. And then our latest is the 9th generation, the ZF90 module, and then also we have this as the RCB, this kind of timing card product for easier installation. And this generation now is multiband, so this is our first generation of multiband receivers. Clear improvement in the time accuracy. Now 5 nanoseconds can go down to 2.5 in so-called differential timing mode. And otherwise, still the two time pulse outputs configurable, and the timing features and the integrity features, of course, now expanded to multiband operation. Okay. And then on the last slide, I put some contacts where you can find some additional information and contact u-blox sales, technical support forum, product information, product documentation, and also the webinar that I mentioned is in the YouTube. So this is also available for those interested.
So I do have a question on your previous slide, and that's what are the assumptions for the accuracy? Because I'm assuming when you put the timing accuracy, is that assuming, for example, that you're getting a signal from so many satellites, or is it in a multiband? Is it assuming that you are getting multiband? So I'm assuming there are some assumptions in order to achieve that accuracy.
Yes,
at
of
a high
course.
level.
Like yeah, of course. In datasheet, you always assume good conditions. This is what you can expect when you have a good antenna under clear sky. Yeah.
Okay.
So one thing about this RCB F9T, like I don't know if you've seen our time card. So our time card basically uses the open source time card that we have. Like we're using actually the RCB-F9T. So one thing I noticed with this is you have the survey mode, but when you put on the survey mode, you basically will get the results and the survey in, and then after that you have to automatically basically come back to the normal, that's a timing mode or something, and then use basically the outcome that the survey in mode had. I
Mhm.
wish like there was like an automated way that like, let's say the assumption is only like, okay, now I put the antenna, I'm not gonna move it. So I turn this thing on, it goes on survey, and let's say after 24 hours, it switches back to normal. Okay, I wish this was a little bit less like with the need for hand holding. Would you comment on that?
Maybe best to contact the technical support, but you can configure this in a different ways. I mean, if you know the coordinates, you don't need to run the survey in every time. You can configure the receiver so that
No, I
when you
wanted to
boot
have
it up,
more like a plug and play thing. You put it there, you don't touch it, and everything is, every time you turn it on, everything works, you know, but it goes to the survey automatically or something.
yeah, you can configure it to so that it will go to surveying on the boot, or you can configure it to go to fixed coordinates in the boot. So,
and then
yeah.
another thing like that I got it, I think Dotan left already, but like there are a lot of like, let's say people work with me, the interface is very hard. The interface is so counterintuitive. Like the product is fantastic, but the interface makes it extremely hard to do, like find where things are. And then I think from version 8 to version 9, you guys changed basically how the configurations are. Like, and then another thing like I was hoping I will get from this event is anything about the 10th generation?
So far, the 10th generation products we launched, they are not timing products. They are for a consumer application.
Okay.
Yeah. But
so
this
there's
was
no RCB-F10T, right?
No. But yeah, this feedback, maybe we can take it offline. But if you have any ideas or suggestions how to make it more
For sure.
user friendly, those would be welcome. Yeah.
Absolutely. Okay, thank you very much. Like anyone else, any more questions?
I have a question. Quick question.
Go ahead,
Mhm.
In your presentation, you had two tables, table 23 and 24 for single band ionosphere dominates and multi-band ionosphere can be mitigated. So I'm not sure
this
if the resource you provided has these two tables. So I'm not sure where exactly you got this number.
You mean this table?
Yeah, these two tables, table 24, 23, I don't see them in Galileo OS SDD file. You provided
Really?
a source for this information, and I'm not sure from where you got these numbers.
I took it from there, but maybe they have updated the document since then, because this slide is a little bit old.
The one you provided is version 1.1. The one before, which is the most recent one, I think, but neither this one or the one before that has this information. So I would be interested to find out how did you get these numbers, especially the one you marked in red.
Yeah. So what I did, I took this from this document. Yeah. But I took it quite some time ago, so maybe it is changed since then.
What I'm saying is these documents, they have table 23, they have table 24, but these two tables in these documents do not have this information.
Okay.
Yeah, perhaps it changed. Like Samuli, maybe you can give Hisham the version that you have.
Exactly. Yes. All I need, just tell me from where you get these numbers.
Yeah, perhaps as Samuli said, Hisham, maybe that this like, because this document doesn't look like it has any version identifier. So perhaps they updated it now, another table 2324 or something else perhaps now taking that spot.
Yes, fine. If you can just let us know from where you get this information, that will be great. Thank you very much.
Sure. Yeah, that would be great. Like Samuli, if you have that document, perhaps you can give it to us. We can also put it with the alongside with
Yes,
the presentation there.
exactly. Even better idea. Thank you, Ahmed.
You're
Yeah,
welcome.
I can check it tomorrow. Yeah.
Yeah, thank you.
If I may just jump in for a second,
Absolutely, Thomas. Absolutely.
the table 23 and 24, as they're displayed on the screen, appear to be identical to what's in the version of the document 1.0, which has now
Okay.
been superseded by version 1.1.
Ah,
And I'm just comparing what's on screen with what's in version 1.0, and I see that the two tables, the values that are in red are identical. So my assumption is it was taken from the 1.0, and the new version 1.1 maybe has the same URL as the one that's on screen.
yeah, yeah. Hisham, is that clear?
Oh, that's what, so it is 1.0, not 1.1, which is the one mentioned here in this
1.1
slide. Okay,
superseded 1.0. So this what you see is from
Okay.
1.0.
thank you very much.
You're welcome.
Okay, that was cleared quickly. Thank you.
Anyone else for our marathon people here? Wojtek, Dan, Greg, we're calling everyone. Alon,
No additional questions.
great. Okay, without further ado, Samuli, thank you very much for the session, and thank you everyone for sticking around. And we'll have the recorded session basically on the wiki.
Okay, thank you.
Okay, thank you everyone.
Thank you.
Enjoy the rest of your day, night, wherever you're in around the globe.
Thanks.
Thank you.
Yeah. Bye bye.